So let's talk about PV equals RTN. And more specifically, we're going to go into kind of talking about energy, and specifically kinetic energy. Right, and so kind of bear with me here. This is going to be a long conversation, but specifically, we're going to be looking at temperature. So remember that temperature is energy. Whenever I add energy to the system, in case like say I add heat to the system, I start heating up a can. I don't know if you remember Soda Can Crush, but here's my can of soda. I start heating it up. I start adding energy with this, right? And when I start adding energy through the form of heat, I'm going to be raising the temperature. And so that means temperature is really just a measurement of energy, or it's some sort of energy. And so when we're talking about energy, remember, I'm not sure if you covered this way back in the day, but remember there's different types of energy, right? We got chemical energy. So the energy stored within our bonds, that's stuff like food, right? We have gravitational potential. So that's kind of like if you're at the top of a roller coaster right here, you have a lot of gravitational potential energy. We have like kinetic energy. So instead of down here, you're down here and you're moving with a lot of this, a lot of speed, basically. And then we also have thermal energy. So in this sense, when we're taking a look at our little can here, we're adding thermal energy to this, right? And we are heating this up, and we know that thermal energy is being acquired because we start to see vapor. In any case, let's talk about what's actually happening in the can. So here we have liquid water, and here we have vapor. The molecules inside liquid water are kind of dispersed, and think back all the way in Module 1, where we had you draw like what a liquid looks like in terms of molecule, versus what is vapor. Vapor is a gas, right? And so you know that these gas particles are going to be more spread out, and they are going to be moving a little bit faster, right? And so these molecules, we'll just draw like a small molecule of water here. These molecules are vibrating. They could be moving around, so moving left and right, and then they could also be rotating, right? You don't really need to know this. This is just kind of how molecules have their energy. And this is kind of pertinent into what we're going to be talking about today, which is temperature, right? Remember that temperature is a form of energy, and we're kind of determining how much energy there is in a system. That being said, when you touch something, you feel its temperature. You can feel it's either hot or cold. Now, I'm not sure if you've ever heard this saying, but there's no such thing as cold. That looks like coid. But there's no such thing as cold. It's just the absence of heat. But what exactly is heat? Right, so let's take a look at this, right? Vapor obviously has more energy. It's going to be hotter than just regular liquid. So if you put your hand up to, I'm not an artist, right? But that's your hand. So you put a hand up to your vapor, and what's happening here and what you're going to be feeling is you're going to feel a lot of those water molecules kind of slamming into your hand. And they're going to be slamming more frequently, and they are going to be slamming with more strength. And so we don't really feel hot. We just feel the frequency at which these kind of objects slam against the surface. And that's what we interpret as hot. But in reality, it's just the molecules are moving faster than they used to be. And so they're slamming more constantly, which kind of like heats it up. So think if you kind of clap slowly versus if you clap faster, right? Your hand kind of gets hot. And that's kind of what we interpret as, heat or cold. So in this sense, we've kind of established that thermal energy is kind of that, right? So that's a measurement of how constantly these molecules are going to be slamming against your hand. And these are specifically moving molecules, and that's why I kind of went over to the kind of like the rotational, translational, and vibrational energies, right? And essentially when you add more energy into the system, you're going to either make them rotate more, move more, or vibrate just a little bit more. So in any case, these are always moving molecules, right? And I'm not sure if you've taken physics before, but we know that the energy of motion is kinetic energy. So kinetic energy is basically 1/2 mv squared. This v is squared. And so essentially this is what it is, right? Realistically, this is just a long-winded theory behind why whenever we're talking about mv squared, we need to look at the relationships for this. As mass goes up, volume goes down, right? Because these are assuming at the same temperature, right? So this is at one temperature, well, just temperature T, right? If we increase the volume in order to make T constant before and final, right? We're going to have to do something opposite, right? And so you can see that because these two are being multiplied against each other, they have an inverse relationship. Let's try to connect this into kind of pavoraton. PV equals RTN. When P goes up, V has to go down, right? We know that. When P goes up, V goes down. Same thing here. When M goes up, V goes down. They are inversely proportional. Or we can do the other flip side, right? When you have less massive kind of molecules, in order to exert the same temperature as other molecules, if they're less massive, then they need to be moving a little bit faster, right? And that's really all you need to know for, this is currently the fall 2021. And for Dr. Salpe's fall 2021, this is probably the extent that you would have to be able to know, right? Just know that when mass goes down, velocity goes up. When velocity goes up, or when velocity goes down, mass has to go up. They're just inversely proportional. Again, start thinking about this interactions between pressure and volume. Essentially the same thing. But how will you see this on the exam, right? So you might have seen this problem on this exam, and this is kind of your markers and to know how to actually interpret this. So we have equal masses of O2 and HBr, so O2 and HBr, and we have equal masses of it. Now I'm going to say that we have 32 grams of O2, 32 grams of HBr, because, we can interpret this however we want. And so essentially, if we have 32 grams of O2, we have 1 mole of O2, and that's taken by getting our molar mass. And HBr, we have roughly 0.4 moles if we have 32 grams, right? Just remember your conversion between grams to moles. Now, whenever you have this, we also know that we have equal volume and temperature. So volume and temperature are going to be equal. And so we're looking at what statements are true. Now, let's take a look at our statements, right? We have pressure. So the one thing that we know that includes volume, temperature, and moles is PV equals RTN, or your pavoraton, right? So we're going to need to use that. We have molecules, right? So where are we going to get molecules? Well, remember that we have moles, and we can easily convert between moles and molecules. Just kind of multiply this by the Avogadro's number. Avo number. And we are going to be talking about kinetic energy and what else? Velocity, right? So that's why we kind of went through that whole winded explanation about using 1/2 mv squared. Because if you're just looking at this, pavoraton, we're not worried about velocity. There's no way that we can actually get velocity. But kind of remember that this kinetic energy is roughly equal to temperature, right? And so in this scenario, temperature is kind of related to this kinetic energy, and we'll set them equal because we're not given any more information. Anyways, let's start breaking this thing down, right? Let's start bottom to top, just because we're feeling that way. The pressures of both gases are the same. Well, let's take a look at this pavoraton, right? If we have to isolate pressure is equal to RTN over V. We know that N is a big factor. And the only difference between this O2 and this HBr, the only difference between that is not T, not V, not R, and only N, right? And so we can see that by canceling, let me write that down again. We have RTN over V, right? And we can cancel, because these are going to be the same, that pressure is related to how many moles of gas there are. And we know that they're not equal. O2 has more moles of gas than HBr does. So we know that they're not going to be the same. We know that pressure of O2 has to be higher or greater than the pressure of HBr. All right, let's talk about this. The average kinetic energy of HBr molecules is greater than that of O2, but we said that kinetic energy is roughly equal to temperature. Let's take a look at this. We have equal temperature. There's equal temperature and volume. So we know that obviously that's not going to be true. The average velocity of the O2 molecules is less than that of the HBr molecules. Remember what we were talking about here. When mass goes up, velocity has to go down, right? And so when we're saying that if the velocity of O2 molecules is less than that, that means that O2 molecules has to be more heavy or more massive than this HBr. Is that true? Well, no, right? O2 has a roughly 32 grams versus HBr, don't quote me on this, I'm going to say it's roughly 80 grams in molar mass. And there is a big disparity between this. Again, that's how I got this 1 mole of O2 versus 0.4. So we know that, in fact, if it was the other way around, right, if this instead was saying, instead of less, but more or greater than, this answer would be true. But we know it's not. There are more moles of HBr molecules than O2. Let's look at answer letter B. We know that's not true, right? Because we have more moles of, we have more moles of O2, which means we'll have more molecules in that. Which leaves us with A, right? The pressure of O2 container is greater than the pressure in the HBr container. Let's take a look at this, right? Remember how pressure and number of moles are directly proportional? We can see that O2 does in fact have more moles than HBr. So this is obviously the right answer, so 6 is A. Now this is kind of how you're supposed to tackle these types of problems. Just kind of write down everything that you know. It may be a little lengthy. Again, it just comes, this is a little bit overkill, right? But you can kind of see how we started using this Pavo-Raton, and we also use this 1/2 mv squared because we're given kinetic energy, also velocity. All right, so that concludes this kind of mini lecture. Feel free to rewatch it again if you need to. But yeah, we'll see you in the next one.